Oh. All right, well, let's get started here. Page 27. We'll take our look at the calendar. Today, lesson or class number 30. Today is theorems about differentiable functions. Coming up on Monday, I will hand out our fourth take-home quiz, which you will do and give back to me on Wednesday. In class on Monday is our project check-in day. As usual, you will get the most out of that day by trying to be as close to the recommended calendar for the two projects as possible. And then on Wednesday coming up is our related rates in-class quiz. You don't need to worry about studying for that. That is going to be the only group quiz of the entire semester, of 2 semesters. If you take Calc 2 with me, this is the one and only group quiz. So you're going to work with everybody to solve that problem on Wednesday. All right, and again, the 2 projects are due right after Thanksgiving. It looks like the Monday and Wednesday when we come back. Sure. Any questions? Any questions on the calendar? Okay. Yes. Thursday, Friday, no school. Wednesday is a regular class day. Yeah. Okay. All right. So before we jump in on page 27, one quick announcement. Not about the square root of 2. There is an off-campus group that's coming on campus to help students just like you either create your own resume or update and improve your own resume. It is a free workshop, but requires you to register ahead of time. And so it's on December the 5th, which is a Tuesday, noon until 1:30. The URL for this webpage is long. I have made a tiny URL. It is right up here. Write it down, and it will bring you right to this website right there. So photo of this or write that down. Free workshop, looks good. Any questions on that? Okay, so let's jump in here on the top of page 27. Another couple of announcements. In the homework that is due today, right, 28 was the one that's due today? But 28 was the previous one about the linear approximations. So we also did quadratic approximations, but there weren't any quadratic approximations in the homework. This was an oversight on my part. I'm not mandating this. I'll give you full credit for doing what you've done for homework 28, but strong recommendation is that you do these 3 additional problems. Either write them down or take a photograph of this. 5th edition, slightly different from 6th edition. And it says over there, ignore the directions in your book. You notice that I'm giving you problems in chapter 10, which is not only not part of Calc 1, it's actually like at the end of Calc 2. So like you're not going to recognize the words in the directions for these problems, but ignore those directions and instead just find the quadratic approximation, just like we did in the activities in class, right? The ax squared plus bx plus c. Take your derivatives, plug in 0 or whatever the number is, and find the values of A, B, C, okay? So 3 other problems. I'm not gonna like technically grade them or check them, but you should do them. And I'll be really explicit on the take-home quiz that I'm gonna hand you Monday. There's gonna be something just like one of these 3 problems. So I want you to be prepared to be able to do that, okay? Questions on that? Okay, also here on the sideboard, there was a problem in the related rates day 2 in the activities. Which had to do with a clock and the hour hand and the minute hand and how fast the distance between them was changing. This is a really difficult problem. I have written up most of the solution here if you want to take a picture of it. I'm assuming most of us haven't looked at that problem because the first task was to finish the related rates homework in class. And that was a big enough task that most people didn't look at the clock problem. But anyway, there's the solution if you want it. Okay, I think that is that. So here we are on the top of page 27. In this class, we discussed 3 theorems about differentiable functions: the mean value theorem, which is new, the racetrack principle, which is also new, and the increasing function theorem, which is old. Now, this guy right here is in the even more practice, and today's activity is pretty long, so probably not going to see it in class, and if you don't look at the EMP, you'll never see it. It's okay if you never see it. But anyway, I'm making a promise here, and I want to make sure that you know that it's in the even more practice. Okay, some of today will be a bit more theoretical than usual. I say some, pretty much all of today is a bit more theoretical than usual. We are going to be strengthening some new math muscles, some different math muscles. Most of our class, Calc 1, is about calculations, calculating a derivative, solving for a tangent line being horizontal. This is not a calculations class. This is a theoretical class, and it'll be the first opportunity for many of us to really write proofs. And writing proofs is a skill, and if it is brand new to you, it is going to be a skill that requires work to get better at. It is going to be crucially important as you do the activities today to read carefully every single word and symbol in the activities. I know it's easy to just sort of skip ahead to the formula and just say, oh, I know what to do, I see the formula, but really read carefully. It's going to put you in a good position to be able to write proofs for possibly the first time, okay? All right, here we go. The mean value theorem has a hypothesis and a conclusion. The hypothesis is the condition that we want to sort of open the door to the theorem. And if we happen to have that condition being satisfied, then the conclusion comes through. I'll write a simple one over here. If the weather, you don't need to write it, but if the weather is nice, I will go for a run. Suppose this is a promise that I'm making to myself. The hypothesis of this theorem is the weather is nice. The conclusion of this theorem is I will go for a run. Here are all the different possibilities for the truthness or falseness of each of those things. They could both be true. The first one could be true and the second one could be false. And vice versa. The first could be false and the second could be true, or they could both be false, okay? And we got to make sure we understand, like, what is this statement really saying? If I make this internal promise about my exercising. Okay, suppose that the weather is nice, just like it is today. What am I promising I will do? I will run. Suppose that the weather is nice and I don't run. I have broken my promise, right? I have made this statement false, like I've broken this promise. Suppose that it's crummy outside and I go for a run. Have I broken my promise? No. It doesn't say anything about what to do if the weather is crummy. It only tells me I'm promising if the weather is nice. So if the weather is crummy, I could go for a run. It's fine. I haven't broken a promise. If the weather is crummy, I could choose not to run. I have also not broken my promise in that case, okay? So, what's that? Exactly. Of the four possible things we just talked about, there's only one of them that breaks this statement. That's if the weather is nice, just like today, but I don't go for a run. That's the only way that I've got like a contradiction to this statement. Okay, so let's take a look at the mean value theorem. The hypothesis, which is highlighted up there in yellow, f is a function which is differentiable on an open interval a, b. So that just means it has a derivative for every point in this interval, for every x value between those two numbers. The conclusion, there is at least one number c between a and b such that f prime of c is equal to f of b minus f of a over b minus a. All right, that theorem looks like a lot of gobbledygook. Let's take a look at a picture and all will become clear. Suppose that we've got our function right here. This is our function f or f of x, okay? It is differentiable. A and b are my two x values marked on the x-axis. This function clearly has a derivative at every point in between a and b. There's no corner, there's no vertical tangent line, there's no asymptotes, it's not discontinuous anywhere, which means that the yellow thing is satisfied, right? If it's a nice day out, I'm going to promise to do something. If you have a function which is differentiable, I promise you something will be true. So here's a function which is differentiable. So here's the promise. There's at least one c between a and b. So there's some c someplace. I'm just going to arbitrarily put it like over here. I don't know where it is yet, but just to be concrete, there is some c between a and b so that the derivative at c, okay, that's a geometrical thing. What does that represent geometrically? What about the tangent line? What is f prime of c? What characteristic of the tangent line? It's the slope of the tangent line, right? Okay, so let's go up here. So we got c, like it's got a point on the curve, and there is a tangent line, and it has a slope, is equal to, okay, let's separately consider the right-hand side. F of b minus f of a over b minus a is a formula you've seen before. Geometrically, what is that in this picture? It is a slope. Slope of what line? It's not drawn yet. The secant line, the line connecting the point at A and the point at B, right? There's a line that connects those two. And to say the two slopes are equal, which is after all what this is saying, it's saying the slope of the tangent line is equal to the slope of the secant line from the start and end. To say that two lines have the same slope means they are what? Parallel, right? If you have two lines with the same slope, we know they are parallel. Okay, Are the two lines that I've drawn up here parallel? No, okay, that wasn't where C was located. But there is a C someplace. It wasn't here, but it's someplace. Yeah, so we just gotta kind of slide a little bit to the left here. We're just looking for some tangent line that is parallel to that secant line. I don't know, maybe somewhere around there, right? There is a C. So if that's in fact the right one, then this is actually where the number C is. But do you believe it? Like no matter how that picture looks, if you draw your secant line, there's going to be some tangent line that's parallel. Right? It's reasonable. So I don't have that equation memorized, but I understand there's some tangent line parallel to the secant line. And based on that, I can write down that equation, okay? All right, that is the mean value theorem. So named not because like it's angry or anything like that. Mean in this case means average, right? The average rate of change is the slope of the secant line. That is a defined phrase in math, the average rate of change. So the mean value theorem, the average value theorem. Okay, coming down here, number 2. Two zombies, Goethe and Hertz, start a race in the same location. If during the race Goethe was consistently shambling slower than Hertz, what can you conclude? Let's have our starting line right here. I do love zombies. What's not to love? All right, so we got on here. Okay, so we've got Goethe there, and we got Hertz there, right? And like two dead folks. And they start the same race at the same location, and Goethe was consistently shambling slower than Hertz. So what can you say about their relative positions at every moment in this race? Who's winning? Hertz is, did I do that backwards? Sorry. Hertz is winning, right? Because Goethe was going slower at every possible moment. There's nothing surprising in this, right? They start at the same place. If one of them is faster the whole time, then they're going to be winning the whole time. Okay. Same idea here, two zombies. They complete a race in a photo finish. So I'm not telling you they're starting at the same spot. I'm saying they're ending at the same spot. So let's end them at the same spot. G here, H here. Same as before, Goethe was consistently slower than Hertz. Same speed kind of thing. Who was winning this race the entire time up until this tie? Goethe was winning the whole time, right? The only way that they can finish at the same time, if Goethe is always slower, is if Goethe had a head start and was ahead the entire time up until this moment right here, right? So Hertz was behind from the beginning, had a head start of some kind, and caught up only at that last moment right there at the finish line, okay? All right, let us translate all this zombie stuff into functions. To say that Goethe is slower, well, let's see. That feels to me like a rate of change. So what symbol am I putting in between here? Like if G prime represents Goethe's speed and H prime represents Hertz's speed, if Goethe is always slower, less than, yeah? Slower. I'll put an equal, like maybe they are the same speed. That's not what the zombie thing says, but in our theorem, it's going to be a less than or equal to. And to say that they were tied here at the beginning, like if we're saying like I've got a race here and like A is like the beginning X, and we'll say that B is the ending X. To say that they were tied at the beginning means that they were in the same spot at A. So do you guys buy that's like a reasonable way to write they started the race in the same location? Compared to down here, they ended the race in the same location. And so what we said in this first case was that, how was it written? Was that Goethe was behind the entire time, right? And so here's our theorem. If G and H are two functions that are differentiable on an interval AB, and G prime of X is less than or equal to H prime of X, Goethe is moving slower than Hertz, and G of A equals H of A. They start at the same spot. Then G is always what? Bigger or less than H? Less. I'll put it equals as well. Okay. G is always less than or equal to H. Okay. other part of this same theorem called the racetrack principle. G and H are two functions differentiable. Goethe is slower than Hertz, that's what that says, same as before. But now they don't start at the same spot, they end at the same moment. Then who was winning the whole time? Up here, if they end up tied and Goethe is slower, Goethe had to be ahead the entire time. Goethe was bigger than Hertz, faster, farther ahead than Hertz at every single moment. Okay, so what are you supposed to do with these two things in a mathematical sense? Clearly, it's not about zombies, but hopefully the zombies convince you that these two theorems are true. Like, it makes it reasonable that these two things are true. So you're going to use the racetrack principle several times in the activity. I'm going to point out one other thing before I set you ahead on the activity. There is a video, it's like 8 minutes long. Again, that's another tiny URL kind of thing, but this is just a YouTube link. Just didn't want to write out all the YouTube URL. And so if folks are interested, I'm happy to like pull that thing up here right after class, but if you don't have 8 minutes after class and you don't want to see it right now, I'd encourage you to check it out later. It is an application of the racetrack principle. So let's move on to the group activities. Again, read every word very carefully.